Some of the most fundamental rules in all of science are all about a world we can't even see, the world of gases. It's just this invisible chaos of countless tiny particles bouncing around at insane speeds. So today, we're going to see how a few simple observations about this invisible world led scientists to a single, powerful master equation that brings it all together.
So here's our game plan. We're going to start with the simple rules that gases play by, then we'll meet the individual laws themselves. After that, we'll see how they all combine into that one master equation. Then, and this is the really cool part, we'll dive into the particle theory that explains why it all works. And finally, we'll see how our ideal model stacks up against the real world.
For centuries, scientists were kind of like detectives. They were just watching how air and other gases behaved when you squeezed them, or heated them up, or just added more. Now, they couldn't see the individual particles, of course, but they could totally see the effects. And from all these observations, they started to figure out this set of incredibly predictable rules, or laws, that seem to govern how all gases behave. To get a handle on these rules, you really only need to know about 4 key players. First up is pressure. That's the force the gas is pushing with. Then you've got volume, which is just the space it takes up. Temperature, which is really a measure of the gas's energy. And listen, this is super important, it has to be in Kelvin for these laws to work right. And finally, N, which is the amount of gas you have. We measure it in moles, which is basically just a chemist's way of counting a ridiculously huge number of particles. Think of it like a dozen, but for atoms.
All right, so let's get into it by meeting the individual laws that scientists started to piece together. Each one is a crucial piece of the puzzle, and each one zeroes in on the relationship between 2 of those variables while keeping everything else the same. These are the building blocks for the whole shebang.
First up is Robert Boyle, way back in 1662. He was the one who figured out that if you take some gas and hold the temperature steady, its pressure and volume are totally connected, but in an opposite way. So, in plain English, if you squeeze a gas into a smaller container, its pressure skyrockets. Just picture squeezing a sealed balloon, right? As you make its volume smaller, you can feel the air inside pushing back way harder. Yep, that's Boyle's law right there.
And this graph shows that relationship perfectly. Just look at it. As the volume along the bottom gets bigger, the pressure on the side drops down along that smooth curve. It's so predictable that if you double the volume, you literally cut the pressure exactly in half. Okay, fast forward over 100 years, and a scientist named Jacques Charles finds another major piece of the puzzle. He discovered that if you keep the pressure the same, the volume of a gas is directly tied to its temperature. So, you heat a gas, it expands, you cool it down, it shrinks. This is exactly why a party balloon might look a little sad and shrunken if you take it outside on a really cold day. And this illustrates that relationship beautifully. See, unlike Boyle's curve, this is a perfect straight line. As the temperature goes up, the volume goes up right along with it, in perfect lockstep. And what's really fascinating about this graph is if you trace that line all the way back, down to where the volume would be 0, you actually find the idea of absolute zero, the coldest temperature possible in the universe.
And finally, we get Amedeo Avogadro's big idea. And honestly, this one is probably the most intuitive of them all. It just says that if you keep the temperature and pressure the same, the amount of space the gas takes up is all about how much gas you have. More gas particles, well, they just take up more space. Simple as that. And here we go again. Just like with Charles's law, we see another clean, straight-line relationship. It's solid proof for Avogadro's idea. You double the amount of gas particles, you double the volume they take up, as long as that pressure and temperature don't change. It's just beautifully simple, isn't it?
So we have all these separate little rules, right? Connecting pressure and volume and temperature, and volume and the amount of gas. They're all pieces of a puzzle. Now, let's see what happens when we snap them all together into one single, elegant, and incredibly powerful master equation.
Okay, quick recap. Boyle's law ties pressure to volume. Charles's law ties volume to temperature. Avogadro's law ties volume to the amount of gas. Each law gives us one part of the story, and you can almost see the pattern forming right in front of you. Each one of these laws is a clue. So you can imagine the next big question for scientists was, what if these aren't separate rules at all? What if we could combine them all into one grand unified theory of gases? And there it is, the ideal gas law. PV equals nRT.
This is the master equation. It wraps up all those other laws we just talked about into one neat package. Pressure times volume equals the number of moles times this special number called the ideal gas constant, which we call R, times the temperature. It connects all four of our variables in one single beautiful statement.
Okay, so an equation on a slide is great and all, but what can you actually do with it? Well, it turns out this can be a matter of life and death. Let's take a super practical example from scuba diving. A diver absolutely needs to know how much breathable air is in their tank, not just its physical size, but how much air it's going to give them under the crushing pressure of being deep underwater.
We can figure this out using a handy version of the law, often called the combined gas law. It's perfect for comparing a gas under two different sets of conditions. So first, we look at the initial conditions in the tank. It's a 13.2-liter tank, but it's at an incredibly high pressure. Then we look at the final conditions, the much lower pressure at the diver's depth and their body temperature. You plug those numbers into the formula, solve for that final volume, and the result is just mind-blowing. That small tank provides 667 liters of air for the diver to breathe. That right there is the power of this equation.
So far, we've looked at the rules of how gases act. But you know, science is never satisfied with just the rules. It always wants to know the reason. Now that we know the what, let's pull back the curtain and finally understand the why by diving into that invisible world of particles.
Now, this understanding didn't just pop up overnight. Oh no, it was a long, long journey. It really kicked off with Daniel Bernoulli back in the 1700s, who first suggested that gases are just a bunch of tiny particles whizzing around. And then, over the next century and a half, these absolute giants of science, Clausius, Maxwell, Boltzmann, they built on that simple idea, turning it into a powerful mathematical theory.
And that's what we call the kinetic theory of gases. It's this amazing model that says everything we can see and measure about a gas, its pressure, its temperature, all of it is just the large-scale result of trillions of tiny individual particles in constant random motion. And that motion is the secret why behind all the laws we just saw.
Now, to make the math manageable, the theory starts by making a few simplifying assumptions. It basically describes a perfect or ideal gas. It pretends the particles are just tiny little points that don't take up any space themselves. It assumes they bounce off each other and the walls like perfect billiard balls, never losing any energy. And it pretends they don't attract or repel each other at all. With this simplified ideal picture, we can finally understand why the laws work.
This quote from the philosopher John Locke just nails the revolutionary idea at the heart of this whole theory. What we feel as heat isn't some weird mysterious fluid, it's just the average kinetic energy, the average speed of all those gas particles. And that one idea explains everything. It perfectly explains Charles's law. When you heat a gas, you're just making its particles zip around faster. They smack into the walls of the container harder and more often, pushing it outward and making the volume bigger. And it explains Boyle's law too. If you squeeze that same gas into a smaller space, those particles have less room to fly around, so they're going to slam into the walls way more often. And that faster rate of collisions is exactly what we measure as higher pressure.
So we've got this beautiful, elegant law and this incredibly powerful theory that's all based on a perfect ideal gas. But how does this perfect scientific model actually hold up in the messy, complicated real world?
Okay, this slide really breaks down the differences. An ideal gas, well, it's just a concept, a hypothetical thing we use for our models. A real gas is what's actually floating around us. In reality, gas particles do have a tiny bit of volume, and they do exert these tiny little forces on each other. So what does that mean? It means that while the ideal gas law is a fantastic approximation under most normal conditions, like the air in the room right now, real gases start to, well, misbehave a bit when you get to really high pressures or really low temperatures, where those particles get all squished together.
And that brings us to the big final question, doesn't it? If no gas is truly ideal, why is this law so incredibly foundational? Why do we spend so much time learning it? Well, it's because scientific models don't have to be perfect to be powerful. The ideal gas law gives us a simple yet remarkably accurate way to understand the fundamental behavior of matter. It's the essential starting point, the foundation on which all the more complex understandings are built.